This video is brought to you by Nippon Chemi-Con. Hi, I'm at Kanagawa Research Center of Nippon Chemi-Con. The last collaboration with Nippon Chemi-Con received a lot of positive feedback, so we collaborated again. Today, I will be making my own aluminum electrolytic capacitors with full support from Nippon Chemi-Con Research Center. I'll be making electrolytic capacitors from raw materials. I'll even wind the foils by hand. How much is the performance of a hand-winding electrolytic capacitor different from that of a commercial product? Can I make a decent capacitor? Let's see if we can find out. Now, let's get started. Before actually making an aluminum electrolytic capacitor, let's review its structure first. This is a standard aluminum electrolytic capacitor. The blue part is a sleeve. If you disassemble it, there are two parts. This is the internal element of the aluminum electrolytic capacitor. It was placed inside this case, just like this. As you can see, the element consists of wound films. I illustrated the basic structure of an electrolytic capacitor: an anode foil, a separator, and a cathode foil. This part is filled with electrolyte. The material of the anode foil and cathode foil is aluminum, and the separator is made of paper. Because the films are made of aluminum, it's called aluminum electrolytic capacitor. The anode and cathode are aluminum foils. Chemical treatments are applied to the foils: etching and forming. Firstly, in order to increase the surface area of the foils, both the anode and cathode foils are etched. Etching increases the surface area. It's a process to melt the surface of the aluminum foil, creating fine holes or pits. You can't see how the surface area increased with the naked eye, but using an electron microscope, you can see it clearly. After that, the anode foil goes through the forming process to raise the withstand voltage of the electrolytic capacitor. In the process, a dielectric layer is formed on the surface of the aluminum foil. In this case, the dielectric is aluminum oxide. Then the treated aluminum foil and separator are wound together. Once they are impregnated with electrolyte, an aluminum electrolytic capacitor element is complete. Each of the anode foil and cathode foil has a capacitance. The total capacitance of the two connected in series is the capacitance of the electrolytic capacitor itself. Now I'd like to start making electrolytic capacitors. What you need to do first to make an aluminum electrolytic capacitor is to pre-process an aluminum foil. I'm going to apply various treatments to this piece of aluminum foil. I'm going to use hazardous chemicals in this process, so I'm wearing a pair of safety glasses and a white coat. Let's start pre-processing. The purpose of this process is to remove the natural oxide layer and oil layer from the surface of the aluminum foil. I'm going to put this aluminum foil in the liquid here, then wait for about 1 minute. Today, I'm going to make electrolytic capacitors with 35-volt withstand voltage. The treatments applied to the aluminum foil changes according to the withstand voltage. Each electrolytic capacitor manufacturer has their own way of pre-processing. Here I'm using a common method. Common pre-processing methods use alkaline or acidic liquid to immerse the aluminum foil. What am I using today? It's a secret. The pre-processing is done, so I'll rinse the aluminum foil. I'll rinse the surface with pure water. It's done. If you proceed to the next step right away, the water on the surface of the aluminum foil will affect the composition of the chemical solution in the next step. It's completely dry. Now pre-processing is completed, let's go to the next step. Once the aluminum foil gets cleaned, you need to quickly move on to the next step before it forms oxide on its surface. Here, I'm going to etch the aluminum foil. The reason why electrolytic capacitors have a larger capacitance than other capacitors is because the surface area of the aluminum foil is large. I'll soak the foil in this etching bath. This will create fine pits on the foil's surface. The pits don't go through the aluminum foil. When those pits are created, the surface area of the aluminum foil is expanded. The foil is being etched in this bath. The bath contains hydrochloric acid-based solution. If you want to make a capacitor with a low withstand voltage, treat the anode and cathode foils with alternating current. Etching was completed just now. I'll pull up the aluminum foil. Then, wash it. Because it went through the etching process, the foil lost its shine. The surface looks a bit rough. If you see the surface using a microscope, you can see fine pits on the surface of the foil. By filling these pits with electrolyte, you can make the best of the large surface area. This is the surface image of the aluminum foil I etched. The foil surface was smooth before the etching process, but after the process, there are many pits on the surface. Now the etching process is complete. Let's proceed to the forming process, also known as anodic oxidation. This aluminum foil has a large surface area thanks to the etching. Now we'll form a dielectric layer on it. The dielectric I'm going to form is aluminum oxide. This forming process is usually only necessary for the anode foil, which requires higher withstand voltage. But sometimes cathode foils are treated as well, such as when making an electrolytic capacitor with higher withstand voltage. An oxide layer is formed in the forming process. If this oxide layer is thick, the withstand voltage will be higher. If the oxide layer is thin, the withstand voltage will be lower. However, if the oxide film is too thick, the pits created in the etching process will disappear. Then, you won't be able to make use of the expanded surface area. Therefore, it is extremely important to form the oxide layer while keeping the balance between the withstand voltage and the surface area. Here is the aluminum foil. I'll put it in position. What's in this tin? It's ammonium adipate. It's generally known as organic acid. I'm going to dip the anode foil into the acid. When you apply voltage, the forming process begins. After turning on the power supply, we'll wait for approximately 30 minutes. This process is time-consuming. Now the forming is done. Let's take out the foil. The color has changed a bit. When the forming process was completed, the metallic luster on the surface disappeared. This is because a dielectric or aluminum oxide was formed on surface. The forming process is finished. The next step is to cut the aluminum foil into the size that fits to an electrolytic capacitor. Due to circumstances, I prepared a sheet that already went through up to the forming process. Forming process is already applied to this aluminum foil. It's like a cooking show. Processes up to forming are very difficult, so I couldn't be sure if I can get a good quality foil for this video. I'll place the foil here, then cut it in the middle. The case size of the electrolytic capacitor I'm making today is 25 millimeters. The capacitor element will be wound up and put in the case, so the element must be smaller than the case. Now let's actually slice the foil. The width must be 17 millimeters. I was able to slice the foil. Next, let's calculate the length of the aluminum foil. I'll calculate the length of the foil necessary for the target capacitance. Then, I'll select the case for the foil. The longer the foil is, the larger the capacitance will be. I decided to cut the foils to 18 centimeters. According to the calculation, the capacitance of an 18 centimeter foil will be 872 microfarad. It's the capacitance of the anode foil. The capacitance of the capacitor will be the total of the anode and cathode foils. I'm guessing it's going to be around 800 microfarad. Now I'm going to cut the anode foil. I want the length to be 18 centimeter. Around here. There. It's done. Here are the foils I cut. I made several strips. Next step is to attach lead wires to these strips. The wires will stick out from the capacitor as electrodes, so you need to connect the aluminum foils and lead wires by stitching. I'm going to connect wires to the foils using this machine. Let's start. Firstly, I'll put this anode foil in the machine. The foil's placed in the machine. This machine has many levers. Push the one that presses down the foil. It's done. Then I'll put the lead wire in here. The foil and the wire are not connected yet. I'll punch holes on a foil. The needle is going through the foil and wire. Now holes were punched in both the anode foil and lead wire. If you have a look, you can see how the anode foil and lead wire were punched through. The next process is to press the area around the hole to put them together completely. Push down the lever, and then there you go. Now the anode foil and the lead wire are connected. You can see how firmly they're connected in this enlarged view. Now I'll just do the same thing on the other foils. I prepared several foils connected to lead wires. I'm going to wind these foils to make the elements. I'm going to make the elements of aluminum electrolytic capacitors. Materials of an element includes this electrolytic paper, the anode foil with lead wire I connected earlier using that machine, and a cathode foil. Winding them together is such delicate work. Moreover, I'm going to do that manually. I know it's hard, but I'll try anyway. There are two separators or electrolytic papers. I'll place the cathode foil between the separators. Adjusting and winding the foil is really difficult. If you don't do it carefully, the element will end up looking like a bamboo shoot. I put the cathode foil in place. Next is the anode foil. The lead wire is the key. I need to position the foils really carefully. The outer perimeter is longer than the inner perimeter, so if you align the lead wires when you start winding, they won't be in the right positions in the end. I place the foils where they will line in the end. Now I'll start winding the foils. I'll turn this lever and good start. Well, I'm actually pretty good at this. I'm surprised myself. I've reached the end of the foils, so I'll cut the electrolytic papers. After cutting, if I stop holding the element, the paper will unwind. To prevent that, I'll use this tape. Put the tape on the element and turn the lever like I did earlier. Then it's done. The element of the electrolytic capacitor is complete. This is the electrolytic capacitor element. I'll attach the rubber seal to the element at the lead wires. It's to seal the electrolytic capacitor. Put the wires through the holes on the seal and set the capacitor on the machine to attach the seal. This is easy. I only pulled this lever down. and the sealing is completed. All I need to do is doing the same for the other capacitor elements. Next, I'm going to make the electrolyte that will serve as the actual cathode of the electrolytic capacitor. By allowing the electrolyte to permeate into the surface of the foil, you can make use of the surface area expanded by etching. There are various ways to prepare the electrolyte, but today I'll use a common method using standard materials, just in case I'm wearing a white coat and glasses. These are the materials: a solvent, an organic acid, and an additive. I'm going to mix them all. I'll put the powder in first. I'll pour one of the liquids. Then I'll pour the other liquid. It's done. Keep stirring using the stirrer until powder dissolves. Now the electrolyte is complete. I'm going to let the capacitor elements impregnated with the electrolyte. Actually, any liquid can serve as electrolyte as long as it contains electrolyte. So today, in addition to the electrolyte I mixed, I prepared another liquid, this black liquid. I'll use this black liquid as another electrolyte. There are 3 beakers. One is for the elements I wound manually. The other 2 are for standard electrolyte in that black liquid. I'll perform impregnation on these 3. Firstly, the elements I wound. The target capacitance is about 800 microfarad. These are the elements wound in the factory. I'll also pour the electrolyte in here. And lastly, the black liquid. It's a carbonated liquid. It's bubbling. I poured electrolyte in these 3 beakers. The next step is to perform impregnation in a vacuum. Let's start. I'll put these electrolytic capacitor elements immersed in the electrolytes into this machine. The machine lowers the pressure. Put in and turn on the switch. The impregnation has started. I'll leave the elements for a few minutes under low pressure inside the machine. Then the electrolyte will permeate into the surface of the electrolytic papers and anode foils. I waited for about 10 minutes. It seems the impregnation is finished. The next step is casing and riveting. Once the impregnation is complete, I'll put the element in this aluminum case. Usually this process includes centrifugation, but today I'll remove the excess electrolyte using a more simple method. Poke the foil with the element several times to remove the excess electrolyte, then put the element in the case. Now it's ready for riveting. Since these capacitors are not factory products, there is a little electrolyte left around the seals. I'll wipe it before going to the next process. Next, I'm going to rivet the capacitors. I have an element in the case here. I'll set it in the machine and turn on the switch. Riveting is done. Now it has the shape of a common capacitor. Once the riveting process is complete, I'll perform a forming process again. The process is called reforming. Capacitors will be reformed in this constant temperature bath. It's really hot in the constant temperature bath. The purpose of the reforming process is to repair the damages on aluminum foils made in the slitting and winding processes. Reforming occurs when DC voltage is applied to a capacitor. I'll apply a little higher voltage than the rated voltage. I set all the capacitors in the jig. Now I'll put it in the constant temperature bath. Wow, it's hot. Let's close the door. After I turn the power on, a lot of current flows for a while. As time passes, the damages on the aluminum foils will be healed. Then the current reduces. This is a time-consuming process. I'll leave the capacitors for about an hour. About half of the reforming process is finished. Let's look into the capacitors. The ones wound in a factory barely have leakage current. This is because the electrolyte repaired the damages of the foils, which means the capacitors were reformed. The ones I wound manually also have almost zero leakage current. That means the surface of their aluminum foils have also been healed. There's a problem with the coke ones. The capacitors in which coke is used as electrolyte. Tremendous amount of leakage current is flowing, about 10 to 20 times as the other capacitors. What this means is that the damages on the surface of the foil are not healed yet. Current is leaking from the damaged areas. Let's wait until the reforming process is finished. Finally, reforming's finished. In the constant temperature bath, can you see? The capacitors are still hot. I'll leave them for a while until they cool down. The reforming process is finally finished. It's been really long from the first process. What we're going to do next is to wrap this capacitor with a heat shrink sleeve. Put the capacitor in the sleeve and heat it with a heat gun. Then the sleeve shrinks perfectly. It's done pretty neatly. It shrunk well. Looks almost the same as a manufactured product. I finally made an electrolytic capacitor. Next, I'm going to evaluate the capacitors by connecting to an LCR meter and using in a converter. Firstly, I'll check the capacitance, ESR, and tangent delta. Then I'll use the capacitors for the output of a DC-DC converter to see if the ripple voltage is successfully removed. Firstly, these capacitors that I made, I wound their elements manually. The capacitance is 808 microfarad. It's good. This is the capacitance at 120 Hz. The target value of the capacitance was about 800 to 810 microfarad. The meter says 808 microfarad. I think I made it pretty well. Today I made 4 capacitors manually. This one's 809 microfarad. It's also good. I might have a gift of winding capacitors manually. This one's 803 microfarad. And the last one is 804 microfarad. All of the hand-winding capacitors seemed of pretty good quality. I thought of the reason why, when you wind the element manually, the positions of the anode foil and the cathode foil usually don't match. But I was able to match the positions quite well. Also, the foils tend to stretch when being wound, but it didn't happen when I was winding. That's my guess. I summarized the capacitance of the electrolytic capacitors I made. The capacitance of the manually wound ones varies a little. It's because they are manually wound. The capacitance of the machine winding capacitors is almost the same. Machine winding is very precise. The capacitance of the Coke electrolyte capacitors varies a little. Now I'm going to check the ESR of the capacitors using this LCR meter. This graph is for the standard electrolyte capacitor. The x-axis is the frequency and y-axis is the ESR. At the frequency of 100 kHz, the ESR was 30 milliohm. The ESR values don't vary for the machine winding capacitors. Machines are really precise. The ESR of the ones I wound manually varies at lower frequency. It seems the winding ability affects the ESR. As for the Coke electrolyte capacitors, ESR at 1000 kHz is 350 milliohm. It's quite high. It's about 10 times the standard electrolyte capacitors. When you actually use the Coke capacitors, the performance will be extremely affected by ESR, I suppose. So far, I've been evaluating the capacitors. Next, I'm going to connect the capacitors to the output of a DC-DC converter to measure ripple voltage. This is the DC-DC converter. The switching frequency is fixed at 150 kHz. The capacitor at the output is the one I made. The load has 10 ohm resistance. A current of about 0.5 ampere is supposed to flow. I'll measure the ripple voltage at the both ends of the resistor. To minimize the ripple voltage, the capacitance of the capacitor must be large. It's an important factor. However, there are other requirements. It is that the ESR or equivalent series resistance and ESL must be small. I'm excited to look into the ESR characteristics, especially of the Coke capacitors. Firstly, the hand-winding capacitor. The capacitance is 807 microfarad. The top waveform shows the ripple voltage, and the bottom shows the current flowing through the capacitor. The switching frequency is 150 kHz. The ripple voltage is approximately 20 millivolt peak to peak. I think it's pretty good. Since the capacitor has some ESR, there is a slightly sharp drop in here. You can clearly see the voltage caused by ESR at the point where the polarity of the current is reversed. My hand-winding capacitor seems pretty good. It seems to be reliable enough for practical use. The measured capacitance is 807 microfarad, and the ESR is 30 milliohm. You can see those characteristics from the waveform as well. Next, I'm going to test the capacitors whose elements were wound mechanically. Same elements, but different electrolyte. The orange one has standard electrolyte in it. The blue one has Coke in it as electrolyte. The capacitance values are not so different. The standard one is 576 microfarad. The Coke one is 545 microfarad. However, the ESR is significantly different. The standard one is 30 milliohm, and the Coke one is 350 milliohm. Coke one is 10 times higher. Let's see the ripple voltage of these capacitors. Firstly, machine winding capacitor with standard electrolyte. Compared to my hand winding one, the capacitance is only about 70%, but the peak-to-peak ripple voltage is almost the same, around 20 millivolt. It seems the ESR and ESL are affecting the ripple more than the capacitance. I enlarged the ripple voltage waveform. There's a slight surge voltage at the point where the switching occurs. It's caused by the ESL. It's hard to find the part affected by the ESR. There are some ups and downs here. They are caused by ESR. You can't see much influence from the capacitance. ESR has more influence. Lastly, the machine winding capacitor with Coke electrolyte turned on power. Well, the ripple voltage doesn't fit in the display. I'll adjust the range a bit. There you go. Coke electrolyte causes huge difference. The standard electrolyte capacitor has about 20 millivolt ripple voltage peak to peak. The Coke electrolyte one has 170 millivolt ripple voltage peak to peak. The ripple voltage is about 10 times higher. The capacitance of these capacitors are almost the same. The difference is caused by the ESR, mostly. This coke capacitor cannot be put to practical use. It's better to use a capacitor with standard electrolyte. With different electrolyte, the capacitor's characteristics change dramatically. This experiment showed how electrolyte hugely affects the characteristics of a capacitor. Today, I visited the research center of Nippon Chemi-Con and made hand-winding capacitors. The performance of my capacitors was pretty good. The capacitance was as good as I aimed for. You rarely get to wind electrolytic capacitors manually. It was more difficult than I imagined. Also about the electrolyte. Today I use Coke's electrolyte. Even Coke capacitors function somehow. It was very interesting. In the description, I attached links to the materials regarding Nippon Chemi-Con capacitors, including datasheet, a document that summarizes the basic knowledge of electrolytic capacitors, SPICE models for simulations, and recruitment information. Especially the document that summarizes the basic knowledge of electrolytic capacitors is a must-read for anyone who uses electrolytic capacitors. You can download the materials from the description. Thanks for watching and see you next time.